Hello and welcome. Today we're going to decode the secret language that scientists and mathematicians use to talk about the universe. From the unbelievably huge to the impossibly small.
So let's start with a question. How do you write a number with, say, 50 zeros without your hand cramping up? It seems like a kind of silly problem, right? But the answer, well, it unlocks an incredibly powerful mathematical toolkit. Okay, let's dive in. Here's how we're going to do it. We'll build this toolkit step by step. We're starting with a simple idea, the power of powers, then we'll look at its opposite, learn the rules of the game, and finally, we'll put it all together to unlock standard form. By the end, you'll be able to write any number you can think of.
All right, first up, let's look at the most basic building block. It's a really simple, super elegant way to write repeated multiplication.
So instead of writing out 6 times 6 times 6, we can just use this simple little notation. We call the big number you're multiplying, in this case the 6, the base. And that small floating number, that's the power or the index. It just tells us how many times to multiply the base by itself. It's a fantastic piece of shorthand. And just look at how much of a difference that tiny little index number makes. Going from a power of 2 to a power of 3 doesn't just add a little bit. Nope, it multiplies the entire result by another 6, which takes us all the way from 36 up to 216. That's some serious growth. Now, there are also a couple of key rules you just gotta remember. These might seem a bit weird at first, I get it, especially that anything to the power of 0 is 1, but they are absolutely fundamental shortcuts that make the whole system work. Trust me on this, they're essential. In math, for pretty much every action, there's an equal and opposite reaction. So, if powers are all about building numbers up, what about breaking them back down? Let's take a look at the other side of the coin. So yeah, if powers are about building things up through multiplication, roots are about breaking them back down to find out where they started. They're basically asking the question, what number times itself gave me this result? It's the reverse operation. And this is a really cool and important difference. Think about it. Since multiplying two negative numbers gives you a positive, right? Like -5 times -5 is positive 25. That means every positive number actually has two square roots. But with cube roots, that doesn't happen. -5 cubed is -125. So you only get one unique answer. Okay, one more opposite idea for you, the reciprocal. The easiest way to think about it is just the upside down version of a number. And what's really slick is how we write it, using a negative power. This is an incredibly clever bit of notation, and it's going to be super important in just a minute. All right, we've got our building blocks. We have our vocabulary, you could say. Now we need the instruction manual, the grammar, that tells us how to put them all together. So what happens when you've got a situation like this? Do you have to work out 4 cubed, and then work out 4 squared, and then multiply those huge numbers together? I mean, you could, but luckily, no, you don't have to. There are some really elegant rules that make it way, way easier. This table right here, this is our cheat sheet. These are the laws that let you simplify really complex-looking stuff in a flash. If you're multiplying, you add the powers. Dividing, you subtract them. And if you raise a power to another power, you just multiply them. But, and this is the crucial part, remember, these rules only work if the base numbers are the same. Let's see it in action, because this is where the magic happens. We just apply that multiplication rule from our cheat sheet, and because the base number is the same on both sides, it's a 6, we can pretty much just ignore it. The problem just becomes 10 plus x equals 2. A really scary-looking equation suddenly turns into simple algebra. That's the real power of these rules. So we've built the whole toolkit. We have all the pieces. Now for the payoff. Let's use everything we've learned to finally write those ridiculously big and impossibly small numbers we talked about at the very beginning. This right here is the universal format. It's called standard form, and it's built on everything we just learned, especially powers of 10. This system is what allows a scientist to compare the mass of an entire planet to the mass of a single atom, using the exact same language. It's brilliant. For big numbers, the process is actually pretty straightforward. First, you just rewrite the number so it's between 1 and 10. So for this, that's 3.24. Then, you just count how many places you had to move the decimal point to get it there. In this case, it was 6 places, so that becomes our positive power of 10. Easy. And for small numbers,
Well, it's pretty much the exact same process, just in reverse. We moved the decimal to the right this time to get 5.67. And because we moved it the other way to describe a number that's less than 1, the power becomes negative. We moved it 4 places, so it's 10 to the power of -4. See? Same logic.
And just like that, there you have it. We've gone from a simple idea, just repeated multiplication, all the way to a complete system for describing the entire cosmos. We started with powers and roots, we learned the grammar that rules them, and we put it all together to create standard form. So now you speak the language of the huge and the tiny. The question is, what are you going to measure? The distance to the nearest star? The size of a single cell? The language is all yours now. Thanks so much for joining me for this explainer.